So once we have the free body diagram with all the forces and moments, just one thing I want to mention, that I said the only time you put a moment on the system is when you remove the fixed support, right? Needless to say that if you have an external moment applied to your system, obviously it should be in your rigid body, right? Some couple, moment of a couple. If there is a moment of a couple in your system, obviously it should be there in your free body diagram too, because it's already there and it's one of the moments applied as an external moment. But in case of removing supports and drawing the free body diagram, taking care of the forces that should be on your free body diagram when you isolate the structure, right? The only type of support that you need to put a moment to compensate for that is the fixed support, at least for just two-dimensional system that within the scope of this part of the course. So once we have the free body diagram with all the forces and moments, we can apply Newton's first law. And we said it before, I'm just going to put it here again. Summation vector sum of all the forces should be 0. So we are in two-dimensional space. This means vector sum of all the forces in x direction should be 0. And sum of all the forces in y direction should be 0. Take one direction as positive, and then doesn't have to be in these directions exactly, but these are the typical directions, depending on what your x, y axes are. And along with that, summation of all the moment at some given point should be 0. Usually take the counterclockwise as positive. And that's it. From this, and having the free body diagram with all the forces in this one, you should be able to pretty much analyze any system. Let's take a look at an example. Let's go with the beam again. So I'm just going to emphasize that these are what you need to use once you have your free body diagram. I'm just going to include the whole thing. All right, let's take a look at another beam. Beams are very important structures in engineering. Over and over, you'll deal with beams a lot later on. And the reason is that, I think I mentioned this before in this course, that in so many cases, you can simplify a system into beams. And once you do that, you know how to deal with beams under different kind of loading and different forces and moments, you can just analyze the system. These are very practical structures. In so many cases, we can simplify our structures into a series of beams connected to each other. All right, let me bring that. Make sure I'm going to bring the right. There we go. So I have this beam. It's supported on both ends, right? They have reactions. We have a pin support here, and we have a pin support here. Now, oh, sorry, this is a pin. I have to mention that in the problem statement, or I can just put it here. This is a pin. I'll emphasize that. This is a pin support. I always tell you what the support is. Is it possible? Sure, of course. In case you want to just double check. I'm assuming this slide you're talking about. Okay. All right, so I have the beam. One side is a pin support. The other side is just a roller. The quality of the figure is not that great, so just put it here. And I always tell you, either it's very obvious. If I go back to the table I have there, it's either very obvious, the roller and rocker cable, you see it in the structure. If it's not very obvious, or it's the pin, it should be pretty obvious. If it's not very obvious, I'll tell you what the support is. Typically, it's pretty obvious. This is not a great, I would say, representation. Or at least, I guess I got a bad quality picture. So the question is, determine the horizontal and vertical components I guess of reaction forces on the beam. There is a continuation at A and B. This makes it more clear. This is point A, and this is point B. All right, first step, always start with free body diagram. If you get the free body diagram right, the rest is very straightforward. Forces. I draw the beam, I'm isolating the beam for this problem. I'm taking this part out, I'm isolating this beam. I'm going to look at this free body diagram. Now forces. I have a downward force 100 newtons, so I'll just put it here. I have that 600 newtons with an angle of 45 degrees on the beam. So these are external forces, obviously should be there. This is 45 degrees. What else? What else do I have there?
The force on the pin at B.
I have the force on the pin, which, what should I put there?
200 newtons.
I have exactly 200 newtons there. It's an external force. There we go. So let me just put all of them, 100 newtons, 600 newtons, 200 newtons. I'm just going to remove this free body diagram I wrote here. It makes it crowded. All right. What other component I should put on this free body diagram? Force of the roller on the beam. And force of the roller is vertical. Just one component. If you forgot that, take a look at the table. So the force of, I'm going to put the force of the reaction forces with different color. So obvious. I'll call this, let's use this color. I call this A, Y. What else? What is the right reaction? What is the right support at point B? It's a pin, right? The pin. So pin, as we saw in that table, and we saw before, when we remove a support, pin support, we have to put two forces, like two components of a force to compensate for that. I'm going to do that. Let me, intuitively, I know it's in this direction, so I put in this direction, but if you put the direction wrong, again, it does not matter. So this would be BY and BX. Yes, Rich. I think I've got all the forces. Now let's start with, now that I have this free body diagram is complete, now I can study this structure. Right? I'll say summation of forces is equal to 0. It should be, because it's an equilibrium. This beam is not, do we need weight? I'm not given the weight. So in this case, I guess they ignored the weight. Usually when there is a weight, either they give you the mass or they give you the weight. So since they didn't say anything, I'm assuming that they're ignoring the weight, considering that the forces applied to the beam are much more than the weight, so they're just ignoring that. But in an ideal case, definitely you have to put the weight there. All right. So in X direction, they should be 0. In Y direction, they should be 0. All right. I'm taking this as positive and taking this as positive. Let's see what we get there. What are the components of X? What do we have? Minus bx, exactly. Bx, and since I took the right direction as positive, so bx, I put minus bx. And I have 600 cosine 45, exactly. Thank you, guys. I feel good about this. That immediately see that. 600 cosine 45 degrees. If you don't see it, here is what we are talking about. If we decompose this vector into its elements, this would be the y component, and it's 600 cosine, 600 sine, obviously, 600 sine 45, and this is its x component, 600 cosine 45 degrees. Hopefully you remember that from vectors. And that's pretty much it. It's equal to 0. How about y direction? Well, what is going on in y direction? So I have ay and by. Right? Both of them I put upward. Ay plus by minus 200. Okay, let's see. Ay plus by minus 200 plus 100, that's also there, and minus 600 sine 45. Let's see if I missed anything. Ay and by upward, minus 200 and minus 100. Obviously, I put the wrong sign. Exactly. Thank you. My mistake. This should be minus 100. Right. You're right, guys. And minus 600 sine 45 degrees. So from there, let's see what we get. I'll get, from the first equation at least, I get something. I can find bx, which becomes 600 cosine 45 degrees. From the second equation, all I get is ay plus by becomes something. If I take all the these to the other side, it becomes how much is that? 300 plus sine 45 is square root of 2 over 2, so it becomes 300 square root of 2, whatever that value is, Newton. This also becomes 300 square root of 2 newtons. Calculator, you can just calculate that. But this would be bx. So I got bx already. Right? I was asked to find the forces in the reaction. I already got bx from this first equation. Now, just before I go further, obviously now I have another equation with two unknowns, ay and by. But I have I'll just put this one here. I have a second equation, moments, that I can use to find that. But before we go further, look at the first equation, minus bx plus 600 cosine 45. If I didn't take bx in towards left, and if I took it towards right, instead of that, I would have had bx plus 600 cosine 45 degrees equal to 0. And I would have gotten this value minus 300 square root of 2 Newton. Right? This minus here is telling me that, well, the direction I took, or this assumed direction, this direction I assumed that bx is not correct, since I got the negative value. So I have to flip it. So this is for the case if I was taking bx in towards right. And that's why I said it doesn't matter in so many cases at what direction you take. you could take it towards right, you would have ended up with a negative Bx for a magnitude of this force, which doesn't make sense. So you had to, basically that was trying to tell you that, oh, in your free body diagram, the direction of the Bx should be switched. So if you take the wrong direction, not exactly wrong, the direction you assume is not the direction that the force is going to have at the end, you will have a negative value. In this case, I could see that most probably it's this way, so I put it towards left. Anyway, so I got the first value, Bx. Happy so far, so good. Now I have an equation that it has two unknowns. I have By and would it still be right if you get a negative? If I get a negative, so Bx would have been minus 300 square root of 2 Newton. You have two options. Either continue all your calculations with negative value. Right, listen to this one. You either continue your calculation with this negative value and assuming that Bx to the right is to the right, let's say that's what you took as your assumed direction. And you got Bx as negative. Either you can continue the rest of the calculation, assuming Bx is to the right, the same assumption you made at the beginning, and whenever you have Bx, just put minus 300 square root of 2, or flip the direction and change the sign to positive and do the rest of the calculation with the flip direction and the magnitude of positive. Hope it makes sense. So I have two options. Either continue with what you were doing, just whenever you ended up using Bx afterwards, use the negative magnitude and assuming the direction to the right, the same assumption you made at the beginning, or correct your assumption and flip the direction, and then use the positive value for the rest of your calculation. Either way works, should work. All right, so the second part, the second equation that I can use. Obviously now I have an equation, Ay and By are both unknowns that I don't know them, so I can't have one equation, two unknowns. I can't solve that. I need another set of equation or another equation. So for that, I'll take a look at moment. Now, where should I take the moment about? At any given point on this beam, no matter which point you consider, it's here, it's here, pretty bad. It's here, it's here, it's there, anywhere on this point. If you write the moment equation, the moment about that point should be 0 because this structure, the whole structure is in static equilibrium, right? But there is a specific spot on this point, on this beam, that makes your life much easier if you use that. Can someone tell me which point? I can write the moment about any point, but there is one point that if you write the moments about that point, it makes your life much easier. Richard, yes, it's point B. And the reason for that would be I have most number of unknowns, or at least at this point, I can get rid of one of the unknowns. I could write the equation around any point, like let's say somewhere here, the middle of the beam. But then in my moment equation, I had both Ay and By. But if I write the equation of moment either about point B or point A, because Ay is passing through point A and By is passing through point B, I get rid of one of them, depending on which point I'm writing the equation about, which is good because then I'm going to have just one known in my equation. So I'm going to write it about point B, but you could also write it about point A in this case. So you could get rid of Ay. Let's see what happens if I write it about point B. So about point B, I'm writing it about this point. So let's see, 200 newtons, the line of action passes through point B. I get rid of that. Bx, the line of action passes through point B. Remember, moment is created when a force has some distance from the point we are finding the moment about. If there is no distance and the line of action is passing through that point, the moment is 0. So 200 is not creating any moment about point B. Bx is not creating any moment. By is not creating any moment. I'll go all the way to 100. That 100 is creating some moment. What is the moment of 100 Newton force about point B? So it's obviously the force 100 times the distance that force has from point B, which is 2 meters, right? Exactly, Richard. 2 meters, so 2. And it is positive right-hand rule, right? 4 fingers toward along the line of action, palm of your hand towards the point that you're finding the moment about. When you make a fist, the direction would be the same as the counterclockwise, which is positive. We took it as positive. Going to 600 newtons. 600 cosine 45 has no moment about point B because its line of action passes through B. I didn't draw it properly. This force should have been all the way up to here. So these components are exactly in the middle of the beam. We're assuming that the beam is just a line. There's no thickness. We're not given any thickness. So 600 cosine 45 is line of action passes through point B. I don't need to be worried about that. 600 sine 45 though. 600, and I'm just going to write it as 300 square root of 2. What is the distance it has from point B? I'm multiplying this. I'm finding the moment about point B for all these forces I have in this structure. So 600 sine 45, which I replaced it with 300 square root of 2, times 5, exactly. So it's like 3 here, 2 there. So this point, the distance it has from point B is 5. It's 5. The direction of the moment still would be positive. It's downward, counterclockwise. Anything else that we have here? So
I have a question.
go ahead, Dylan.
So you said the x direction of 600 newtons goes through point B, so there's no moment, right?
Exactly.
But the force is 0.2 meters from the center of the beam. So
given. You're right. You're totally right. I actually missed that. So scratch that, guys. Thank you, Dylan. You pointed that correctly. You are actually given the thickness of the beam. How easy, I even missed that. Thank you so much, Dylan. So I was trying to just get rid of that force. Apparently, that force is not that easy to get rid of. There you go. Thank you for that. I was just going all the way by myself, assuming that everything is correct. So it is given the distance. The distance is actually given here as 0.2 meter. So technically now, I have to take that into account. So this force, 600 cosine 45, its line of action, all the way to here, has some distance from point B, and that is 0.2 meters. So I have to take that into account. No way to get rid of that, I guess. So can someone tell me what would be the moment of that force about point B? Right, we have 600 cosine 45, which I'm going to write it as 300 square root of 2. The distance I already said is 0.2, so that is obvious. You guys tell me about the direction of this. Negative, right? Hopefully everyone can see that. The direction is this way. Well, I don't know, probably I'm mirrored in this video. The direction is this way, and the palm of my hand should be from the line of action that my 4 fingers are following to the point that I'm finding the moment about. Goes this way. If I make a fist, my 4 fingers are going to go towards, are going to show the direction of the moment. And in this case, it's going to be clockwise, so this becomes negative. Right? Stop me if you don't see this. Well, and also stop me if there is something I don't see, as Dylan did, which I appreciate that. That 0.2 was there. That was tricky. All right. What else? What else do I have there? Did I take everything into account? AY. So AY is there. What is the distance it has from point B? It's the length of the beam. 3 plus 2 plus 2, which is 7. And the direction or the sign for that, well, the force is upward, palm of my hand towards point B. That's the moment it creates, and it's clockwise, so it would be negative. This becomes 0. So hopefully we took everything into account. Now, looking at this equation, the only unknown is AY. Right? So pretty much you can easily just take, do this math and find AY from this. Like 100 times 2, 200 plus 1500 square root of 2 minus 0.2. Yeah, I cannot do that. I have to take a look at my notes, see what the final value is. So the final value you'll get, if I did all the math correctly, should be 319.5 Newton. That would be the value for AY. So I got BX, I got AY. Knowing these AY, I can go back to this equation, right? This one there, and call it equation star. So from star, now I can find BY. BY would be, well, 300, 1 plus square root of 2 minus 319.5. This, if I did the math right, should give you 404.77 Newton. That would be BY.